Point one, logical form and logical equivalence. An argument is a group of reasons to use to show that an idea is true. The final statement is called the conclusion. The statements that come before it are called premises. If you look at an example, premise number one is all humans need water to live. Premise number two is Maria is a human. So the conclusion will be, therefore, Maria needs water to live. So we can picture this like this. So the premises are the building blocks. They are the reasons. These two are the reasons. And then after we read the reasons, we come up with a conclusion. So conclusion is the result for these reasons. So we're going to take a look at these two arguments. These two arguments, they have very different content, but their logical form is the same. So we're going to use letters like P, Q, and R to understand their form. We're going to also use not P, which is the negation of the P. So let's look at, this is argument one, this is argument two. They have completely two different content, but we're going to understand that the logical form is the same. So argument number one is, if the bell rings or the flag drops, then the race is over. So if you just label them as P, Q, and R, if the bell rings is the P, the flag drops is the Q, the race is over is R. So P or Q, then R. Now, if you also look at this expression with not P, which is not the case that P happens. So we're going to look at this one. We're going to start from the end. If the race is not over, then the bell hasn't rung and the flag hasn't dropped. So if you look at this one, that's what? Not R, then not P, not Q. So let's take a look at a different argument, which is a different content. So the English sentence is, if x is equal to 2, or x is equal to negative 2, then x squared is equal to 4. So for this argument, P is x equals 2, Q is x equals negative 2, then x squared equals 4 is the R portion. So when we look at this, therefore, when we look at the not R, not P, and not Q, so we're going to say if x squared equals 4 is not equal to 4, then x is not equal to 2, and x is not equal to a negative 2. So the argument comes in the form of P or Q, then R. Therefore, we can take a look. Not R, then not P, not Q. Okay, so here it says these two arguments, they have two different content, but their logical form is the same. We're using letters like P, Q, R to make this clear, to represent the component sentences. And then we let the expression not P refer to the sentence. It is not the case that P, and you let the symbol, this one stands for that one. Okay, so P or Q, then R. Therefore, not R, not P, and not Q. So again, the summary is here. The common form of the argument is, if P or Q, then R. Therefore, if not R, then not P, not Q. When we look at the next portion, which is about identifying logical form, we're going to take a look at an example here. The directions are, we're going to fill in the blanks so that the argument B has the same form as argument A. And we're going to represent the common form of the arguments using the letters to stand for the component sentences. So here is the sentence, if Jane is a math major or Jane is a computer science major, then Jane will take math 150. So if P or Q, then R. Now, when we look at these arguments, the reasons, Jane is a computer science major. Therefore, Jane will take 10154. So remember the directions. We're going to fill in these two blanks so that the argument, this new argument that they're going to give us, has the exact same form as the Jane's argument. And we're going to write it as a compound sentence. So here's the thing. It is given that if logic is easy, which is the same part as Jane's a math major, or Jane's a computer science major. So if logic is easy, or I say this argument here, or I will study hard, then I will get an A in this course. So I need argument 1, argument 2, and a conclusion here. So if logic is easy, which is argument 1, or I will study hard, which is argument 2, then I will get an A in this course. So this needs to be I will study hard, and this needs to be I will get an A in this course. We're going to look at what statement means. A statement, or another name would be proposition, is a sentence that is true or false, but not both. So when we have a statement, it is true or false. For example, when we look at this example, 2 plus 2 equals 4, and 2 plus 2 equals 5 are both statements. The first one is a true statement because 2 plus 2 is equal to 4, so this is a true statement. But 2 plus 2 equals 5 is a false statement, but they both represent a statement. However, this one, x squared plus 2 equals 10, 11, it depends whether it is false or true. What are you picking for x? So if you pick a value for x here to satisfy the equation, it will be a true statement. But if you pick something that doesn't work, it will be a false statement. So a statement is only true or false. And when we look at compound statement has these keywords in them. So P but Q means, so here the English word but, it will be represented as and in logic. So P but Q means P and Q. Neither P nor Q means this is neither P, this is a negating the P, nor Q, this is the not Q. So neither P nor Q means in this logic class, not P and not Q. So P but Q means P and Q. Neither P nor Q means not P and not Q. So this symbol here, it means not P. And this symbol here, it is the representation for and. So whenever you say this, this means P and Q. And this V shape here is called the or. So this means P or Q. So we need to know all the definition of these symbols, the meaning of these symbols. This is not P, this is and, this is or. P but Q is P and Q. Neither P nor Q is not P and not Q. We're going to have some questions on the assignments that we're going to translate from English to symbols. So here's an example. We have these two sentences, and here we're going to let that H is it is hot, S is it is sunny. So this English sentence, it is not hot, but it is sunny. So it is hot is H. It is not hot is not H. So the first part is not H. But we'll change it to an N. It is sunny is S. So when you say it is not hot, but it is sunny, this is not hot, and but will change with an and statement. It is sunny is S. This is how we're going to get the answer. Not hot is not H, but is N. It is sunny is S. Now when we look at part B, it is neither hot nor sunny. It is neither hot nor sunny. Remember, neither P nor Q is not P and not Q. So neither hot, so it's not hot, and it's not sunny, so it's not S. And we're going to combine them with an and. So this is what this English sentence is going to be written in logic, not H and not S. We also have to know how to change these inequalities to the logic statements. We have to know the meaning of these two inequalities. X is less than or equal to A means X is less than A or X is equal to A. So we have to know that when we have less than or equal to, we're going to use the keyword and it means that X is less than A or X is equal to A. But whenever we have this compound inequality in the form of A is less than or equal to X, X is less than or equal to B, this means A is less than X, less than or equal to X, and X is less than or equal to B. So this one uses the keyword and this one uses the keyword or. So we're going to explain an example here. Here's the question. The question says that X is a particular real number. We have three statements, P, Q, and R. So P is 0 is less than X is less than 3 is the Q, and X equals 3 is the R. So we have three problems here. We're going to write these three problems in logical form. So the first one is X is less than or equal to 3. So first we need to write this out. This means X is less than or equal to 3 means X is less than 3 or X is equal to 3. Then if you go find the relative correspondings for these statements, X is less than 3 is the Q, or is the species, and X equals 3 has been given to us as R. So the answer to part A is Q or R. For this question, 0 is less than X, X is less than 3. So the first thing is we're going to have to find the meaning of this inequality. So the meaning of this inequality is 0 is less than X and X is less than 3. So 0 is less than X is given in the problem as P and is upside down V. X is less than 3 is given as Q in the problem. So the answer for part B is this in this box, P and Q. The last one is 0 is less than X and X is less than or equal to 3. So first, the meaning of this inequality is 0 is less than X and X is less than or equal to 3. Now I'm going to find the letter corresponding for this from the problem. So the letter corresponding for this one is P and is this symbol. The letter corresponding for this one, it's not given already. Well, we worked on this in part A. So you can also work on this again if you want to. Whenever we see this inequality, it means X is less than 3 or X is equal to 3. And this one is Q, this one is O, and this one is R. Or since you already worked on this part along in part A, you could just copy your answer from part A, and this will be the answer for the part C of this question. Now we're going to look at the truth tables. So we have two things that we're going to learn here, conjunction and disjunction. If P and Q are statement variables, the conjunction of P and Q is P and Q, which is denoted as P and Q. It is true when and only when both P and Q are true. If either P or Q is false, both of them are false. If P and Q are the variable statement variables, the disjunction of P and Q is P or Q. So or is disjunction, and is conjunction. And this is how we are going to show an or statement with this V symbol. It is true when just one of them is true, or when both of them are true, and it's only false when both of them are false. So for or to be false, the criteria is both of them has to be false. For and to be true, they both have to be true. So these are the notation for Java, C, and C++. They use the following notations. This is not, and this is how these computer languages using it. For and, this is what they're using. They use the double ampersand. And then this is or, and this is how they express the or in these computer languages. If you look at the truth table for this exclusive or, so this whole thing by itself is called exclusive or. The meaning for the exclusive or is you just have to pick one of them, not both, not none. So here's a real world explanation. This whole thing is called exclusive or, and the meaning of the exclusive or is you can pick cake, which is P, or you can pick ice cream, which is Q. The deal is you can have one, but not both. If you take both, the rule is broken, which is false. If you take none, nothing is chosen, it's also false. If you exactly take one of these, this is the only allowed case, and it will be true. So let's look at the truth table, how they came up with these results by using the truth table. So we need a P and a Q. So here's the P column, here's the Q column. And then if you list all the possibilities for P and Q, they can be both true, or P can be true and Q can be false, or P can be false, Q can be true, and both of these letters can be false. So these are the four possibilities for P and Q. So first we're going to look at P or Q. For P or Q, true gives me true, true false gives me true, false true gives me true. For false, we will get false because remember the or statement, or is only false when both of them are false. So or is false just one time, and or gets just one time false, and when both of the components are false. Every other case, an or statement will be a true statement. So this part is handled. Now we're going to look at P and Q. So remember the rule for and statement. And statement will be true only one time when both of the components are true. So this is an and statement, and it will be true only one time when both of them are true. So only one time true, and the rest of the cases, an and statement will be a false statement. So this is the part for P and Q. But an exclusive or is P or Q and not P and Q. So now this is P and Q, but we have to negate this. So this is like not P and Q. So if we just negate all these true and falses, we will get false, true, true, true. So this is how we get the not P and Q part. Now, this column, we're going to look at the truth table for this very first column, P or Q, and this column. So since it's an and statement, it only gets true when both of them are true. So they only get true here. And also they get, both of them, they have true value here. So these are the two cases that this statement is going to give us a true. And everything else, it will be a false. So this whole thing is here in logic class. It is called exclusive or. And the meaning for the exclusive or is, if you take both the cake and the ice cream, it's not okay. If you take the cake, it is okay. If you only take the ice cream, it is okay. If you don't take any of them, it is not okay. So this is called exclusive or. If you look at another truth table for another question here, so this is the end goal here, and we're going to look at another truth table, knowing that for and we have to have both of them to be true. In all other cases, it will be false. For the or problem, it gets false just one time if both of the statements are false. So we're going to look at the truth table for this question. So P, Q, R. Because here in problem we have P, Q, R. So P and Q and R, they can be all of them can be true. This is the second case. Only R can be false, only Q can be false, and only P can be false. And now we can start look at the options that two letters will be false. In this case, it is Q and R false. In this case, it is P and Q are false. And in the last one, we will have the P and R to be false, and finally they can be all false. So when you have 3 variables, you have 8 options to the third power, 2, 4, 6, 8. So you have 8 possibilities when you have 3 letters. So since we're looking at the truth table form, P and Q or not R. So let's look at the truth table for only the parentheses part first, P and Q. So this is true, because it's an end statement. False, 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 false. Because for n to be true, only if these two are true, so it only becomes true 2 times. Now, when we look at not R, so these are the possibilities for R. Not R means just change them all to the opposite direction. So we're just changing the truths to the false and falses to the truths. So this is the not R. Now we have a first column and we have a second column. And with these 2 columns, we want to look at their OR statements. So OR is only false when both of them are false. So as long as one of them is true, it's a true statement. So this is true, this is true, this is false because both of them are false. True. This is false because both of them are false. This is true. Both of them are false, so it's false. And this is true. This will be the truth table for PAQ or not R. So we have another definition here is called logically equivalent. So even though question may not look like the same question, some of the questions, they will have the same logical equivalence. So when we look at P and Q, so these are the options for P, and these are the options for Q. So when we look at P and Q, remember it's an end statement, so it only becomes true one time when both of them are true. So this is the only case that they are both true. So this is P and Q. And Q and P, when we look at the Q and P, the order, when you change the order, still, when you get them, both of them true, it will be true. All other cases, it will be false. So even though these two are 2 different questions, they will always have the same truth values because they are logically equivalent. So this is actually, we're going to learn this later. This is called commutative property. When you change the order for an end question, the truth table stays the same. So when we look at the definition here, 2 statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement variables. The logical equivalence of statement forms P and Q is denoted by writing P is equivalent to Q. 2 statements are called logically equivalent if and only if they have logically equivalent forms when identical component statement variables are used to replace identical component statements. So in short, when 2 things are logically equivalent, their truth tables are the same. So let's now show the non-equivalence. So we're going to show that here. These 2 example, our goal is we're going to show that this one and these 2 ones are not logically equivalent. So we're going to have an empty chart here that we're going to fill in step by step. So these are the possibilities for P. These are the possibilities for Q. When you have 2 variables, we have 2 to the second power 4 options. They can be both true, or one of them can be true, P can be true, Q can be true, or they can be both false. So the first thing we're going to look at is P and Q. N becomes true only when both of them are true. So this is a true one. But all other cases will be false for the end statement. Okay. Now, this is not P and Q. So this column will be negated because of this not symbol. So true will be false. False will be true. Okay. So we're done with this. This is what we need to compare with the other part of the question. So for the other part of the question, first we need to find the logical truth table for not P. Not true, that means false. Not true, that means false. Not false, that means true. Not false, that means true. Again, now we need not Q. What is the statements for Q? Not true means false. Not false means true. Not true means false. And not false means true. Now, we're going to end these two columns. False, false is false. False, true is false. True, false is false. This is the only true one. So these are the two columns we're going to compare to check if they're logically equivalent. When we check, this one has false, this one has false, they're matching, but they're not matching in the middle. So we see that whenever we're taking the negate of P and Q, you cannot translate it as not P and not Q. We're going to actually learn as De Morgan's law here. When you are negating P and Q, you must say not P or not Q. So if we change this symbol to or using the De Morgan's laws, we were going to get the equivalent truth table. But because we didn't convert it properly, we are proving here that these two will not give you the same truth table. So when we look at what is a De Morgan laws is, the negation of an and statement is logically equivalent to the or statement in which component is negated. Each component is negated. So here's the De Morgan laws. When you have P and Q, you must negate it as not P, and you have to change the symbol, change the and to an or, and change the Q to a not Q. So this is how we express the De Morgan laws for the and statement. Again, but De Morgan law is also correct for an or statement. Whenever you negate an or statement, you must change your or symbol to an and symbol, and you have to negate each component as well. So I will also just include it here because I was missing it. So when you are negating a P or Q, when you are negating a P or Q, this will be logically equivalent to, so we need not P, and we have to change the or statement to an and statement, and we're going to have to change the Q statement to a not Q statement. So this is how we use the De Morgan laws for an or statement. Here's an example to look at here. We're going to use the Morgan laws, to write the negation of -1 is less than x is less than or equal to 4. So this inequality is given to us. We learned this a couple of minutes earlier in this lesson that this inequality, we can separate it as -1 is less than x and x is less than or equal to 4. So -1 is less than x is the same thing as x is greater than -1, and this is the symbol for and x is less than or equal to 4, we just copy it here. Now, when we need to negate this using the De Morgan laws, so we're going to first negate this. So this is the negation symbol. Also, some programming languages, instead of not using like this, they can also use this as not. So I need not x is greater than -1. Also, I'm going to have to negate this symbol. Also, I'm going to have to negate x is less than or equal to 4. So this is the notation that we're going to negate everything. So when I negate x is greater than -1, its negation is x is less than or equal to -1. Negation of an and is or, and negation of x is less than or equal to 4 is x is just greater than 4. So this is what we get when we negate this. So x is less than or equal to -1 is the same thing as -1 is greater than or x. And that's an or statement, x is greater than 4. This is how we're going to handle this problem by using the De Morgan laws. Now we're going to look at what a tautology and contradiction is. So a tautology is a statement that's always true, and a contradiction is a statement that's always false. So we're going to show in this example that P or not P is a tautology, and the form of P and not P is a contradiction. So P and not P is always false. P or not P is always true. So let's look at the P. It can have two possibilities, true or false. So when we look at the possibilities for not P, when P is true, not P is false. When P is false, not P is true. Now, whenever I create the logical table for P or not P, so if you OR these two columns, OR is true whenever one of them is true. So because always one of them is true, this is a tautology here. And then when we look at the end one, and can be only true if both of them are true, and we don't have that case. So P and not P is a contradiction. So tautology means always true, contradiction means always false. Now we're going to have to learn these laws because the homework assignment, they're going to ask you to read new words. So let's look at a theorem, which is called logical equivalences. Given any statement variables P, Q, and R, a tautology T, in a contradiction C, the following logical equivalences hold. We have the commutative law, which means P and Q is logically equivalent to Q and P. Same thing, P or Q is logically equivalent to Q or P. So maybe you remember these laws from the addition, multiplication. So even if you change the order of the P and Q, you will still get the same logical truth table. This is called commutative law. Next one is the associative laws, which means if you have in a parentheses P and Q, and then you're ending them with R, it will be the exact same result as if you first end the Q and R, then P and Q and R. This is called the associative law of N. If you look at the associative law of OR, when you need to OR P and Q, then when you OR it by R, it will be the same logical truth table when you just do the Q and R's OR truth table first, and then if you create the OR table with the P. Next one is the distributive law. Distributive law is when you have the P ends in a parentheses Q or R, you can just rewrite it as P and Q or P and R. So we can just distribute this P n into two different parentheses. Same thing here. If you have an OR statement, you can just expand it as P or Q and P or R. Without the rules of meaning to be familiar. Identity laws. So whenever you end your P with a tautology, you will always get the P's original truth table. So this is an identity law. Same thing with OR. Whenever you OR your P with a contradiction, which is always a false, then the result will be P. And then if you look at the negation laws, P or not P is a tautology. P and not P is a contradiction. Double negative law, when you take the, when you have not P and taking the not one more time, these two nots will cancel out and you will get the original P. And then if you look at another law here, when you end the P by itself, you will just get the P. If you get the P, if you OR the P by itself, you will just get the P, and this is called independent laws. And then we have the universal bound laws. If you OR the P by a tautology, tautology, you will get the tautologies with this. If you have the P and C contradiction, you will get the C. So we already talked about De Morgan laws. When you're negating P and Q, it's not P or not Q, which is a very important rule. It always shows up on the questions. When you have not P or Q, it's not P and not Q. And then we have this absorption laws, which is this one. Let's understand what this means. Here, you're ending the P by Q, but then you're making an OR statement with P and this. So what happens is it doesn't matter what you have here, because your operation is OR, your result will just depend on what you have on the P. If P has false, and then because when you also end that false statement with the Q, you will also get false. So this will be just equivalent to a P. If we look at here again, so when you have P or Q, but then you're ending it with a P, with an end statement, you will get P, and this is called absorption loss. So P observes the P and Q when you're ORing it. P observes the P or Q when you're ending it. And negotiations of a tautology and contradiction. If it is not a tautology, it's a contradiction. If it is not a contradiction, then it's a tautology. Here's an example that I got from our book. So the book was giving us this problem, and they were saying that simplify this expression using the logs. So the first thing we're going to do is here, when we are taking the not P and Q, we're going to apply the De Morgan's theorem here. When I take the not P and Q, I need not P, change the end to an OR statement, and change this to a not Q. And then copy the rest, and P or Q. So first step is we just apply the De Morgan's law by saying that I need to negate this, I need to change the end to an OR, and I need to negate the Q. So we just apply De Morgan's law. And then here we see two negatives, two nots. So those two nots, they will cancel out, and we only get the P here, and we will copy the rest exactly the same. So what we just applied here is the double negative law. When we have double negative, you just get the P by itself. Now, when we look at this question, this one has P or, this one has P or. So using the distributive law, we can rewrite this as P or parentheses not Q and Q. This is called the distributive property. So when we look at this parentheses, if you change the order, if you write the Q first, keep the end, keep the not Q, this is called the commutative law for the end. We can change the order. The truth table is not going to change. So this is the commutative law. And then we keep the P and OR part the same. So Q and not Q will always contradict. So this is the negation law by end. So this will give us a contradiction. Now what we have is P or contradiction, which will be just a P, because for the OR statement, it's an identity law. If you look at the table, identity law here, here is given as when you have the P or a contradiction, you just get the P by the identity law. If we summarize this section 2.1, an end statement is true when and only when both components are true. An OR statement is false when and only when both components are false. Two statement forms are logically equivalent when and only when they always have the same truth values. So logically equivalent means they have the same truth table. And we have a very important law here called De Morgan's law. It says that when you're negating an end statement, it will be logically equivalent to an OR statement where each component is negated. And when you are negation in an OR statement, it will be logically equivalent to an end statement where you are negating each component. A tautology is a statement that's always true. A contradiction is a statement where it is always false.